Hello, I am back to making Chem2B videos. I'm going to start off where I left off in chapter 12 still, but on the atomic line spectra, which is one of the quantum mechanics problems that are issues that you learn about in this class. So for the phenomena of the atomic line spectra that couldn't be explained with classical physics was about electrons and the lines emitted by different elements when light are shown on them. So the whole idea of the atomic line spectra is about how objects at a high energy state can shine light, and then so objects can absorb light or energy when photons of light are shown on them, and they can do the opposite when they're in a high electron. I'll draw it out. So these are the different energy states that electrons can have. So we start at the lowest one, n equals to 1. Then the second one right here, n equal to 2. Then the third one, which is n equal to 3. And then the fourth one is n equal to 4. And then we'll do one for infinity, n equals to infinity. And the light, or the atom, the element, can go from different states of these energy levels. So the differences between these, as it goes from energy to not, it's called the delta E, which is the change in energy levels of the element, the electron. So when let's say it starts right here at 1, if this element goes up in energy, so let's say it goes from 1 to 4, from n equals to 1 to n equals to 4, then this is called absorption, because it's absorbing energy and it's putting it in a higher energy state. That's not how you spell absorption. And then the opposite, so I'll write the same thing out here, n equals to infinity, n equal to 4. Oh, that's infinity, by the way. Let me rewrite that. N equals to infinity, n equals to 3, n equals to 2, and n equal to 1. If the element goes from, let's say, 3 this time, and it goes down all the way back to 1, then that's the opposite of absorption, which is emission. So that means the object, and when emission happens, light is emitted. So that means the object is going back down to a lower energy, and then in return it gives off light. But the opposite, which is absorption, the light or energy is coming in, and in return it goes to a higher energy state. And that's how the energy levels work. And if you remember, between energy and wavelength of light, so which determines the color, they're correlated. So that means a higher energy of light, which is over here, would have a shorter wavelength, so it would be more like this, while a lower energy of light, remember this is the lower delta E, would have a longer wavelength of light, because the shorter the wavelength, the higher the energy, if you remember that correlation. This idea of the atomic line spectra was discovered back then when light was shown off through different elements, and they all gave different lights. For example, like hydrogen, this is not the actual description of how the lights look. You can look that up if you want to see it. But let's say hydrogen would give off something like this. It would be green, then maybe blue over here. Oh, that's not blue. Redo that. And then over here would be blue, and then over here would be like yellow, and then over here would be red. And then on this side, a different element, let's say sodium, instead of like being at the exact same place where it is, the blue could be all the way up here, then the green farther away, and the yellow really close to the green, and that's not red. And then the last color red could be like right here. And this isn't an accurate description, but like they noticed that different elements showed different energy levels. So the place. So this is the same idea about how different human beings, we all have fingerprints, but different humans have different fingerprints. So just like that, different elements have different atomic line spectra. These line spectra indicated different quantized energy levels for the electrons. And over time, a formula was created to fit the data available for these, the things observed, the line spectra observed by the elements. And the formula is that the energy level, so the change in the energy level, is equal to Z square RH then 1 over n squared. So this is a formula for the energy level, and if you're trying to find what it changed, like it would change from one energy level to another, you use this formula. And this second formula is what you're most likely going to be using in your exams, because it's the easiest formula to ask for a question. So like it'll be like a question could ask, oh, this element went from this level to that level. What? How do you find the wavelength for it, or the change in energy? Then this is a formula you're most likely to use, where you have an option to input two different energy levels. So the first one, which is n squared, the first, I think, initial, and then minus the final, f. And what each part of this formula means, the Z is the atomic number, which is usually going to be 1, because we're going to be using either hydrogen, like lithium 2 minors, or whatever. It's usually, the atomic number is usually going to be 1. So whatever element, like, or ions of an element with an atomic number of 1. And then the RH is a constant, which is going to be given in the exam. And then the N is the energy level. So like up here, it could go from 1 to usually 1 to 5-ish. I don't know if they can be more than 5, but usually you're going to have either 1 to 5. And then this other N is the same thing, either 1 to 5. It's going to be given in the question, and you can use it to find the other energy level. Like I mentioned earlier, the electrons can go from these different energy states. But also, one key thing I forgot to mention was the final state is when n equal to infinity. So let's say the electron is getting absorbed, or I mean, it's moving up energy levels. If it goes past the 4th electron level and it goes all the way to n infinity, that is called being ionized, which means the electron leaves the element. So it goes up to the infinity energy level, which means it just flies away. Like think of it as a balloon flying through different levels of a building. The balloon keeps flying. Eventually, this is the roof of the building. And after it goes higher than this level, you lose the balloon. It goes away and you never see it again. And it's the same thing as electrons. So if this happens on a test where they ask you what happens when it goes to the infinity level, it just means it's ionized and the electron is lost. Now let's do a problem where you have to find one of these energy levels. A problem like this could show up on the exam. So this problem says each spectral line in hydrogen's emission. So we're talking about hydrogen here, which we know has a atomic number of 1. Number equals to 1. Like I told you, the atomic number is usually going to be 1 in these kind of questions. The electron cannot exist in these levels. So basically the question here, we can ignore this and go straight to the question. What color is light is emitted when an electron in a hydrogen atom, once again hydrogen, which has an atomic number of 1, transitions from N4 to N2? So for these ones, for this problem, first we write down the formula to find the change in energy levels, which is Z square RH, and then 1 minus n square of the initial minus n square of the final. So looking at this problem, we can see that it tells a lot. So this could be either an FRQ problem or a multiple part problem, where at first you have to find the energy over here, And then after you find the energy, the question is asking for what color of light is emitted, or the kind of light is emitted. So we have to find the wavelength, the lambda. And if you remember the correlation between energy and lambda, so E equals to H times the frequency. And if you remember from the speed equation, which is C is equal to lambda times nu, which is the frequency, you get nu is equal to C over the lambda. And then since this is here, E is also equal to H times C over lambda. So after we find the E, we have to use it to find the lambda over here. So first we plug it in for the E. So we plug in these values for the E. And the atomic number, we said earlier, 1 times the RH constant, which is given up here, 2.178 times 10 to the negative 18 times, it goes from N4, so the initial, which is 4 square, which is just, we can just write it here to plug it better into the calculator. 4 square is 16 minus 1 over 2 square is 4. And we just plug this into the calculator. After you plug this into the calculator, it gives you a negative 4.084 approximately times 10 to the negative 19. And as you can see here, the number you get is a negative number, which goes along with what we said, which is, when you remember when it's negative, that means energy is, I think energy is given, so it's exothermic, which goes along with this question saying the light is emitted, which means light is lost, so it's exothermic, it's giving off energy. And if you can remember, when it goes from a higher state energy, so N is equal to 4 and N is equal to 2, when it's going from 4 to 2, it's emission, and light is shown. So now we have the energy, we have E equal to this, we plug it into this equation to find the lambda. Since these two are constants that we already know, it becomes negative 4.084 times 10 to the negative 19 is equal to the Planck's constant, which is 6.626 times 10 to the negative 34 times the speed, which is 2.99, or we can say 3 in this class. You can approximate it to 3.0 times 10 to the 8 over lambda. And then we twist this equation to find lambda. So when you do that, it will be 1 over lambda is equal to this over this, and then we flip it. So it'll be 1 over lambda is equal to, actually to make it easier to look at, first I'll multiply these out and get a number. So when I multiply these two numbers, I get negative 4.084 times 10 to the negative 19 is equal to 1.988 times 10 to the negative 25 over lambda. And then lambda would become 1 over lambda is you divide this both sides by this number, so it'll become negative 4.084 times 10 to the negative 19 over this number, 1.988 times 10 to the negative 25. But then lambda, to get lambda from 1 over lambda, you flip it, it'll become lambda on top, 1 on the bottom, which is just lambda, and then that means you have to flip this one as well. So 1.988 would go on the top to the negative 25 over negative 4.084 times 10 to the negative 19. And that's what you get for lambda. And for this problem, since the lambda can't be negative, you just get rid of the negative. The negative doesn't matter. Since E is the negative only tells us that it's exothermic, so it doesn't really matter in terms of finding lambda. The answer, we can write it in positive, is 4.863-ish times 10 to the negative 7. And remember, this answer gives you meters. So we know this is the wavelength, the negative 7. It gives us a wavelength that is within the visual range, so we can actually find the color. So we know this is within the visible light range for wavelengths, so we can find the color, which is in nanometers. And to do that, we just multiply it by 10 to the 9, which is for nanometers. Then when you multiply this number times 10 to the 9, all it does is just move the decimal place 9 times, and then you get 486 nanometers. And if you remember, that is the wavelength for red. So after all this, when hydrogen goes from this to this, you get a wavelength that correlates with the wavelength of red. So as you can see, we went from the transitioning, we went from the atom, the electron transitioning from levels to the energy, then from the energy, and then we went to the wavelength, and from the wavelength, we got the color. So you can tell now there's a correlation when an atom emits a light, you could find the color from the light. So you can do a problem like this when it pops up on a test. I went back to double check it, and turns out I was wrong. So it wouldn't actually give us red, it would give us blue-green, which is violet. So not red. Red is more in the extreme, so red is between like 600 to I think 700 to 800. And then the lower end would give us violet or blue-green, not red. So I would have got this question wrong if I was given it on a test. But then the good news is they wouldn't ask you specifically, because you're not supposed to know the ranges for colors. I think they could just ask you like, what type of light would this give? And if you find this and transfer it to nanometers, you can see this is within the visible range, visible light range. But you don't have to specifically know the color unless they like give you a color chart with the wavelength, and then you can just look at it and know what color you end up with. But for this answer, it's violet because we ended up with this wavelength.